Okay, this video is on non-parametric Anova, and if we're conducting reason to conduct an Anova to test for equal group means across 3 or more treatment levels or treatment groups, and if we find that we've violated the assumptions, then we find ourselves in a non-parametric situation where we would conduct a Kruskal-Wallis test. This works kind of like the Wilcox test. It's a rank sum, but there's actually some drastic differences too. Guys, let's think back to Anova assumptions. The assumptions are independence, normality, and homogeneity of variance. Literature has shown that the violation of these 2 assumptions is not as severe as the violation of independence. Tricky part is, for the non-parametric Anova, we need independence. So we would have to find some severe threat to the other 2 assumptions to find ourselves in a situation where we would need to conduct a non-parametric non-parametric Anova. Now, what I've done is I've created a situation where we may not necessarily, man, I'll tell you what, my computer's running really slow. We may not necessarily reject the normality and equal variance assumption, but I'm giving you a situation here similar to what I did in the Wilcox example, where we've got Likert scores, and I've got this across district, and let's just say this is Central District, this is the East District, and this is the West District. So this particular observation right here had a sum of responses from Likert scaled or Likert response questions, and they're from the West District. Okay, now the first thing we would want to do is we would want to rank our scores, just as we've done before. So I can come over here and do this and go to data and sort, expand the rest of the selection, and you can see that we put these in terms of zeros, ones, and so on and so forth. Now the next thing we need to do is, as we saw in the previous, is we need to rank these. And I'm going to take a shortcut here and do our ranking from 1 to 2 and just do a fill down. Because we got a lot of scores here. Last time I had a manageable data set just for the reason of being able to illustrate how the rank sum process goes, but we got a lot larger data set now. Plus my computer's running really slow. Seems like I say that every single video. Guess I'm getting fed up with it. Alright, finally. Interesting. Well, it looks like I'm going to have to do this little by little. Sorry guys, I had no idea. Need some music or something in the background, don't we? There we go. So we have 162 total observations. Now, if we did it the way we did last time, we would see that the first 11 measurements were zeros. So what we would have to do is we'd have to take the average of the 11 So over, what, 11 places, I guess that would be 5.5s. So we would give each of these a 5.5. The next one, we would see that we have 4 12s, so we would give each of those a 13.5. And this would be our total ranks. Well, guys, when we had a sample size of 20, that was manageable to do, right? And it's not manageable to do now. We want to let Excel take care of this for us. All right, so what I'm going to do, I'm going to show you a feature. And so ranking here. If we go equal to, there's something called rank average. And it's really, really handy in these types of situations. What it will do, it will take our score, so I'm going to click A2, comma, and I'm going to run this all the way down to the end of the data set. So I tell it the total, you know, where all the values are that I wanted to calculate the ranking of that score on. Hopefully your all's computer's running faster than mine. Good gosh, this is crazy. Alright, finally. Okay, and then I'm going to give it a 1. Now I'm up here, in case you're right here, and I'm going to hit equal. And what it will do, it will tell me that this score has a ranking of 6. So it's the 6th highest ranking. Now, I want to complete this for all of our data, but what I need to do to be able to make this happen is I've got to go up here between the A and the 2 and put a $sign. And then I've got to go between the A and the 163 and put a $sign so I can hold that measurement steady. Now I'm going to be able to use fill down and get a ranking for all of my data. So I'm going to be able to rank each and every individual, each and every value in the data set. Alright, so fill down. And why is that 6? We got 12. Okay, we got 12 observations. 13. Okay. So we actually get our rankings here. And what I now want to do is I want to keep this steady. But I want to go back and put these back in terms of the district. So I want to group the districts together again. Yeah, you can see that my ranking went wacky here. That's fine. I didn't need it anyway, because I have my rankings right here. Now the first thing I want to do is I want to do a sum for District W. I want to do a sum for District E. And I want to do a sum for District C. I think that was right, East, West, Central. Yeah. So my sum for W is going to be the rankings for W. Why do I know that's not going to work? Okay, guys, this is driving me crazy. This computer is so slow anymore, keeping me from being able to do what I want to do. Okay. So the sum of my W's is 3772.5. Now I want to do my sum of my E's. And this thing's jumping around like... And again, the logic is if these scores are positioned about the same when we rank them, regardless of the school district they're from, then the sum of the ranks should be pretty close to the same if there's no difference in the scores. So 5731, that seems to be quite a bit different, but you know, we'll let the process play its way out. And then for Central, and again, think of these scores as just being, well, these are rankings, but think of these scores over in the left-hand column as just being a sum of some Likert responses. All right. So now we've got our data, our numbers, and I want to write these down. So I have 3772.5 and 5371 and 4059.50, and I have a sample size of what, 162. Yeah, 162. And so the sample size of each one would be 54. All right, so I'm going to need that in just a second. Okay, iPad kicked out on me. Okay, gang. So what we saw here is that the sum of the ranks for West was wow. I think I've got so many videos stored on my computer that it's causing it to run so slow. It was 3772.5. And the sum of the ranks for the East was 5371. And the sum of the ranks for Central was 4059.5. Okay. Now I also know that my total sample size, so the N for W was the same as for East, the same for Central, and that was 54 in each. So cap N will be our total sample size, which is 162. Now, in the previous, the Wilcoxon test, we had a test statistic W, which was the minimum value of the sum of ranks. Minus the mean correction? Well, in this situation, we don't have a W statistic, we have an H statistic. And I'm getting ready to show you how these are actually, this is actually calculated. So guys, what we have here, the H is equal to 12 over N times N plus 1 times the sum from I equal 1 to K. K is however many groups that we have. This is the ranking divided by its sample size minus 3 times N plus 1. So guys, in making our calculations, we're going to have 12. Our sample size is 162. Okay, let me go on the other side. I don't know what it is, but down here in this left-hand part of my iPad, it just won't write. Won't write up here either. Alright, so we have 12 divided by 162 over 163 times 163. Okay. And then we're going to have the sum of our ranks squared yeah, pretend there's a 2 up there. It's I don't know why, but I'm starting to get dead spots. It's really weird. Oh wow. Alright, then we're going to have minus 3 times 163. Now, let's see if we can make this stuff happen. So guys, I'm going to plug and chug on the calculator a little bit, so bear with me. Okay, so for this part right in here, if I made no calculation errors, I get an extremely large number. Now, I'm going to take this and multiply it by 12, and then divide by the 162 times 163. And then ultimately what I'm going to end up here, I'm going to end up with 501.22 minus 3 times 163. And I get 12.22. Okay, hopefully I did that right. So gang, our H, and then we'll of course follow up with a p-value, and of course make the appropriate decision, or at least I hope we do. Now, it turns out these things are again really easy to take care of in R. But the first thing we need to do is we need to first thing we need to do is get the calculator or the computer to respond. Oh, don't you love the spinning wheel? Alright guys, so you know, I've got this going on here. I'm going to, I want to get rid of this. And I'm going to do something a little different this time. I haven't done this before. I've got this in the situation that I want it. So I'm going to do a save as. And we'll just call this, that's fine, district feelings. That seems to work. And I've already got it there, so I'll just replace it. Take no chances. Continue gives you all sorts of opportunities. The next thing I want to do is I want to do my scores across the district. Well, guys, I should have done this. Let's go district. So I'm kind of showing you something a little semi-clever here. Okay? So the first thing I want to do is get my district W scores. And instead of coding this in the usual way, I want to code these in terms of columns. Now, next thing I want to do is I want to get my east. And actually, I'm going to do something again, kind of different here. I'm going to have two data sets open in R. So that was east. I've got both of them east, don't I? And this is actually district W. No, Doug. District C. So you guys are way ahead of me because sure your computer is not running as crazy as this one is. Okay, now what I want to do is I want to come in and get rid of the first three columns. And I want to save this as district feelings 2. Alright, let's shut all this down. Hopefully the computer will run a little faster if I do that. And I've already saved all that stuff, so no reason to do that again. So guys, what you'll see, I've got up here district feelings and district feelings 2. Okay, now I want to go to R and I want to perform the calculations. And you're going to see what I've done. I've done some things before I got here because it takes so long to install some of this. And when I have QuickTime running, R and stuff doesn't run as quickly. So what I did this before I started the video. Nevertheless, we're going to do some post-hoc stuff. I'm sorry, not post-hoc. We're going to do homogeneity variances, Levine's test. So we have to install car. And if you've already got it installed, you just have to run library. We've also got something that's called PGIRMESS. This has to be installed. And then I want you to come in and go library of the same package. And then obviously we're going to set our working directory. Okay. Now, what this is going to allow us to do is going to allow us to do some post-hoc stuff in the non-parametric setting, which is going to be kind of cool. All right, gang, let's make this happen. What I want to do first of all is I want to save one data set as data. So I'm going to read CSV, and I think is it called district feelings or feelings district? District feelings, okay, that's what I thought. And now I want to get another data set, and I'll call it data 1. Of district feelings 2. So I'm going to have two data sets open. Now, the first thing, let's go into this this blindly and think, well, you know, there's no reason not to run an Anova. And I would hope that by now, realizing the way the data was collected is in that it's the sum of Likert measurements, we would know right off the bat that Anova wouldn't be appropriate, and we would need to do some sort of non-parametric analysis. I had a lady in Cincinnati contact me. She was a physical therapist, and they were looking at different mattresses on people who had back surgery, and they had let they had some control groups, and they had some different types of mattresses that people were sleeping on, and in the end they did some questionnaires and did some Likert scale analysis. Well, as soon as she contacted me and asked me if I would if she could hire me to do the analysis for her write-up, because she was going to publish this in some journal that was appropriate for this kind of profession. It was clear to me, without even looking at the data, that I needed a non-parametric design because of the data being from responses from a Likert scale. So let's say we're not thinking, and let's look at some histograms. Well, first thing I'd like to do is be able to look at histograms across school district. So if I look at data 1, it's going to have my values in district W, district E, and district C. So if I do a histogram of district E, where my data is data 1, Okay. Well, that's interesting. Oh, you guys are probably sitting there screaming at me. Okay, let's look at this now. All right, so I look at my histogram of these scores across District D, and that certainly doesn't look like to me that it came from a normal distribution. I'm going to run histogram District W. So from here I got to tell what data set I'm working with. That's decent. That doesn't look like, that kind of actually does look like it may have come from a normal distribution. And that one actually looks like it maybe came from a normal distribution. Now what I'd like to do is look at all of my scores. So I'm going to look at, and let's just bring it up. So we're just looking at data now, okay? So you can see that my data set that I've called data has the presentation more in line with what we typically did. So what I'll do here is run a histogram for feel and tell it that my data is just data. And or to me, it doesn't look like we have violated the threat or or we're threatening the assumption of normality. Well, again, I can I can test this out. Let's run a Shapiro test of feel. And why is that not working? Hold on, guys. Let me look at something here. Oh, yeah, can't type. Okay, now looking at the Shapiro-Wilk test for normality, it says that we have violated, or not violated, but the null hypothesis that the distribution comes, looks like it comes from a normal distribution, has been rejected. So it looks like we're threatening the normality assumption. And let's go ahead and run Levine test across district. And you can see that our homogeneity of variance, that's for the median, so let's correct that. Yeah, it's probably going to be more statistically significant, yeah. So you can see that we are violating the homogeneity of variance assumption as well. But really, guys, I'm just doing this for practice, just kind of to make a point, because we should know that the way our data was collected, that the non-parametric or the parametric design was not appropriate. All right. Let's see. Let me find. I'm not as familiar with these non-parametric tests as I am the others. So, take a little bit of notes on this one. Okay. All right, let's go ahead and run the test. And the way we run the test here is very, very, very similar to what we do with Anova. And I think that actually should take care of it. So guys, you can see that the rank sum test, we're off a little bit on the chi-square. And this is something that I want you to make a note of. The Kruskal-Wallis test, the rank sum test, uses the chi-square distribution. So the test statistic is a chi-square test statistic and not an F as we had in the Wilcox. And we have 2 degrees of freedom. And our p-value shows statistical significance. So guys, it appears that there is some difference for the results of the non-parametric test in terms of feelings across districts A, B, and C. So what I may want to do here, and what I would do, is go in and take a look at a box plot across district and just see if I can eyeball where these differences may be happening. So when I look at this, it looks like when I look at the medians, it looks like the median for E is a little higher. Looks like the median for W. So I really don't know, but I am going to think that I'm probably my statistical, when I do pairwise, that chances are I'm going to find the difference between east and west. I don't know. Let's actually see what happens. So what I want to do now, I want to do a Kruskal multiple comparison. So that's the command for the multiple comparison. And just as you would imagine, I'm going to do field across district. And I want to do a, what's called a two-tailed test. Now, what this allows me to do is it allows me to kind of hold stable the p-value of 0.05, so it's correcting for any inflation of alpha. And what it does, it looks at our observed difference in rank means, and then it gets a critical difference, and it tells whether the difference is statistically significant or not. Now, guys, this approach would be equivalent to carrying out a two-tail test and seeing that our test statistic, if it was above 1.96, we would reject. If it's below negative 1.96, we would fail to reject. In fact, that's it's probably, this is going to be worthwhile for me to get into, to go back to the blackboard and actually show this. So let's say that we were testing just a straight one sample t-test. Well, in the distribution of sample means, we're going to create a reject region and a fail to reject region. So what I've shaded in there would be our reject region, considering we're conducting a two-tail test. And what we could do is we could actually come in here and find the z critical values that separate, kind of serve as a line in the sand to separate the rejection of fail to reject, or I'm sorry, separate the regions of fail to reject and reject. So this is called our critical value. And what I could do, since I have 5% rejection area, this one right here could be found by taking Q norm, 0.975, comma 0, comma 1. And guys, up there, it's just not going to let me write up here. Can't wait till you guys start doing online stuff. Let me write with my finger. So when I do that, I'm going to get something very close to 1.96. So once I get my measurement over here, I collect my sample, what I could do is I could standardize this. And let's say, just for example, that it turns out to be 2.12. Well, back over here, that would be above my 1.96, so I would be in the reject region. Well, guys, R is doing exactly that for the non-parametric test. It's finding the line in the sand for the difference in the rank sums. If I can get there. Okay, and so that critical difference, this 20.3 479 is equivalent to the 1.96, notice that this observed difference is above that, so our statistical difference, or our difference is statistically significant. Now, if I want to do a multiple comparison, now this is a controlled multiple comparison in that it's going to take the first level that we have. And if you go back to our well, actually it doesn't. It just must make some random decision. But what it does here is it takes one group and does two comparisons in this case against that group. So if I had 5 groups, for example, it would choose one of them, it shows in C here, and it would compare it to everything else. That was a function of this two-tailed command right here. If I want to get into a situation where I compare all groups, then all I have to do is run this. And you'll see what happens here. We not only get the comparison from C to E to C to W, but it also does a comparison of E to W. Now, what's going on here? If you think about the more multiple comparisons we make, we inflate the type 1 error rate. Some people think that even though there's the control factor in this, controlling for the inflation of the type 1 error rate, some people still buy into the old school that the less comparisons we make, kind of the less chance that we commit a type 1 error. So some people are like, hey, let's run it, make it happen, so and just do all multiple comparisons and just kind of go with the flow. Nevertheless, if we do, we see that the reason back here in the original test, the one I'm highlighting right now, the reason this was statistically significant is because the opinions in districts C and E and the differences in districts E and W are statistically significant. Guys, your effect size, they're much more difficult to calculate. In fact, I don't even think I've ever seen an effect size produced for a non-parametric Anova in the Kruskal-Wallis. But if we wanted to do that, we could standardize our p-value and divide by the square root of n and get our r value. But the problem with that, I'm not sure that I don't think that would even be appropriate, because we got a chi-square statistic here instead of I don't know. I don't know how I'd want to do that. If I were going to do the effect size, what I would probably do here, a guess at the effect size. I would probably do Q chi, and I would have 1 minus 0.002071, and our degrees of freedom are 2. Okay, why did we not do Q? Maybe it's Q. Okay, Q chi-square, maybe? Okay, yeah, that must be it. What I'm really doing here is just repeating like what we do with QT or Q norm or QF. So that must be what it is. So it's Q chi-square of 1 minus, because we want the area below, and the p-value on chi-square distributions are just in the upper tail, degrees of freedom 2. So it looks like this has a a standard measure of 12.359. So I may want to calculate R here as 12.359 divided by the square root of what, 154? No. What was our divided by, let's just do the length. Of feel. That'll work. So our R is 0.97, so we have a very, very strong effect size here, if that's even the correct way to do this. And I got to be perfectly honest with you here, I'm not for sure that's even right. So, so guys, if you do a non-parametric ANOVA for your final project, then we need to investigate that much closer. All right, so gang, here's what I would say. Write up in APA style. I would say something to the effect that a Kruskal-Wallis test revealed there we go. I revealed a significant difference in feelings about, whatever across school districts. And then I would want to come in, I'm not going to be able to put the chi-square symbol, but you would put the chi-square symbol there, and of course your degrees of freedom were 2. And the chi-square was 12.3597, right? And our p-value was less than 0.01, but not less than 0.001. Okay, post hoc comparisons. Using Pairwise Wilcoxon. No, using Pairwise Wallace. With correction, showed significant differences in districts C and E. .29 and districts E and W. All right, where are we here? 29.60. So, guys, that's the way that I would write this one up. There's one other thing that we could have done, and I'm not really sure this is what I would do. We could actually come in and do pairwise comparisons with the Wilcox test. And what we could do here, we could do feel across district. And let's do a p adjust here. Let's use the home method, and we'll do exact equal f. I think this will work. Yeah. Okay. So this actually comes in and gives us p-values, which would be kind of handy. I wasn't even thinking about that until I actually wrote this up. When I write this up and I see the observed difference, it would really be nice to come in and put a p-value in here. So we can put the p-value here, and we find statistically significant difference between E and C, and between, of course, E and W, like we saw up here. So you may want to come back up here where I have the observed difference and actually put in the p-values. So let me do that. It's not going to let me modify that. So anyway, I would come right back here where I've highlighted this and put that p equal 0.023, and then I would come here for the observed difference and put the p of 0.0016 or 0.002. So I think that would be clearly appropriate to do that. Guys, I think that's all. I can't think of really anything else that we'd want to do. The tough part of running one of these things is going to be telling the story. You find out that when you conduct your study, the quantitative part, running the numbers and getting the numbers, is the quick part. The hard part is writing up the results and telling the story, making everything tie into your lit review, and make your summary make sense and things like that. So guys, that's it's coming. We'll start that process actually in August. So I look forward to it. Guys, take care. That's all on non-parametric ANOVA.